Now, we know that, like I said before, linear algebra has various applications in different fields. Almost every scientific discipline out there, physics, chemistry, computer science, everything. So here I'm going to talk about a small application. As you have heard, that machine learning is a field that we use the most these days for various purposes, and it is one of the most researched field as well these days. So you can simply see this picture and on the right side of the slide. So if you are asked what is in the picture above, you can simply answer the question by saying that it is a picture of a flower. And then again, if you're asked, what are the attributes, let's say, what colors can you see in the picture? You can simply say that I can see red, I can see blue, yellow, and so on. But we can do this as we human have trained our brains. Like when we are born, we don't know the colors, but then we get to know about the colors, and we identify them whenever they appear next. And this has been possible because of million years of evolution and defining different colors and other attributes. But what happens if a computer is asked the same question? How does a computer see this picture? So as you know that computers are not human brains. Computers do not comprehend the same thing a human being does in the same way. And therefore, doing the same task in a computer is not as easy as we can do it in our head, right? So, computers are basically trained machines. We have to train them in order to recognize different attributes and different things like this picture. So the first question in hand would be, how does a computer store the information present in the picture? So what we know is that computers are designed to understand the language of only zeros and ones. That means the binary numbers. If you are given a data, you will the computer will interpret in terms of 0 and 1. Even any number given, let's say 5, the computer will convert it into binary digits, and that is the way of storing data in a computer. So then how can an image with multiple attributes like color be stored in a computer? Simply, this is achieved by storing the pixel intensities in a 2D array or a matrix format. As you know that whenever you're handling a camera or something, it says, let's say, 24.6 megapixel. So it has those many pixels present in the pictures that it will take. So the computer basically creates an array of these pixels, and then these arrays are matrices or matrix, and this matrix can be processed to identify colors and other attributes. For example, the size of the picture, the depth of a color, and etc. So any possible operations one would want to perform on the on this image would be done by using linear algebra and matrices at the back end. So this is one very interesting example of where linear algebra can be applied in a very practical field. Now we'll talk about the evolution in this field. So basically, this we know that data science depends on many different applications of linear algebra, as evidently we have seen one example in the last slide. So there are also machine learning and deep learning algorithms that we use in artificial intelligence, automation, or many different other aspects. So these algorithms, they rely on linear algebra techniques in the back end. These days we have many libraries for different computational languages. We have many libraries that already gives us few linear algebraic tools that we can implement in order to solve these problems. But some people had to develop it, and new techniques are also being developed, new algorithms are being developed, and those are done by using linear algebra. Similarly, here we will just look at two particular examples here. One is called singular value decomposition, which is shortly abbreviated as SVD, and another one is principal component analysis, also abbreviated as PCA. So first, let us look at SVD, or singular value decomposition. In general, it is a technique in linear algebra to factorize a matrix. Now, where do we use it? So two of the most useful applications singular value decomposition are dimensionality reduction and image compression. For example, you saw that picture before. How do we analyze this picture? In a data set of faces, let's say we have 200,000 faces in a data set. Uh, how can we how can we input a machine learning algorithm that could tell us that first, if we assign names to these particular images, how can we just implement a machine learning algorithm that could tell us that if given an image, it will give us the name. So there are many constraints to a picture, like that flower, it has many attributes, right? Similarly, what happens if we try to reduce the number of attributes? Then we can easily solve, or we can easily approach the picture and analyze them. So SVD is used to process, it is used to, okay, so the process of transferring data from a higher dimension space to a lower dimensional space without losing the most important information is called dimensionality reduction. And SVD is basically one of the techniques that we use to do so. And there are a few packages like in Python, we have NumPy that can be very useful in order to deal with such techniques. It is also this technique SVD is hugely applied to signal processing, image processing, and big data, as well as in numerical weather prediction. For example, given the data of how the cloud is looking today, how the wind is, and what is the humidity, we can predict what the weather could be in next 5 days and so on. Another important application is called principal component analysis. So the principal component of a collection of points, that means of a data in a real coordinate p-dimensional space, like you had seen, the graph we had considered was of dimension 2. That means it had two components for each vector. Similarly, if we say p components or p-dimensional space, means each of the vector will have p number of components. P can be anything. P can be huge as well, like I said, a million. So the principal components of a collection of points in a real coordinate p-dimensional space are a sequence of p direction vectors. Now, principal component analysis is a process of computing principal components and using them to perform a change of basis on the data. So what is a basis? A basis, if you're given a vector space, we have a basis. A basis is again a set of vectors, and the vectors present in this set are also lying in that vector space. But the specialty about this basis is that we can use these vectors present in this particular smaller set to create and generate any other vector present in the vector space. So the small number of vectors that we use to generate the other vectors is the set of them is called a basis. Now for a vector space, there can be plenty of basis. So it's not necessarily that there needs to be only one basis. For example, in the two-dimensional space, if you in the graph, if you think of two vectors, let's say the one vector is 1 0 and the other vector is 0 1, then you can simply multiply them with any number and add or subtract them to get any vector, any other vector in that vector space. For example, 1.5 comma 2, you can multiply 1.5 to 1 0, and then you can multiply 2 0 1, and then if you add them, you'll get 1.5 comma 2. So these two vectors, 0 1 and 1 0, they make a basis for the two-dimensional space. Now, likewise, you can find another basis, let's say 1 0 and 1 1, that can also be used to make as a basis of the vector space, two-dimensional vector space. So there can be plenty of vector spaces, plenty of bases for a vector space. Okay, so basically PCA is also another technique that we can use for dimensionality reduction by performing transformation of a large set of variables into smaller one that still contains most of the information in the large set. Now, it is used in making predictive models. For example, if you given a set of prices for milk in a supermarket for last 1 month, and suppose they have varied, so you can somehow predict the price this milk will attain after 1 month. Okay, so we usually create models to predict future results that will happen. That means we predict an event that will take place in the future. Okay, and PCA is very useful to do that. So principal components are often calculated by singular value decomposition of the data matrix. So previously you have seen singular value decomposition, and using that technique, we get a matrix for the data, and then PCA can be applied on that matrix. So it is also used in cluster algorithm. Cluster algorithm is basically if you're given a data set and you find that from their representations, graphical interpretations, you find them that some of the points, data points, are basically sitting close to each other. You can group them because they are sitting close to each other because they have some similar characteristics. So this is called cluster algorithm. We use it to group similar data. PCA is used in cluster algorithm massively. Okay, now there are few steps that we follow to achieve PCA. The first one is standardization. So the aim of this step is to standardize the range of the continuous initial variables so that each one of them contribute equally to the analysis. Now, step two, covariance matrix computation. So covariance matrix is something you obtain from SVD, and covariance is a word taken from statistics. So if some of you have studied statistics, you might already be aware of this term. So this step two, is used to understand how the variables of the input data set are varying from the mean with respect to each other. That is to see if there is any relationship between them, between the variables. And then finally, step three is computing eigenvectors and eigenvalues of this covariance matrix. Eigenvectors and eigenvalues, like I said before, is a crucial concept in linear algebra, as well as the implementation of them is huge, is just huge in computer science and all other fields. And we rely on this concept a lot. So what we do in this third step is basically in order to determine the principal components of the data. Eigenvectors and eigenvalues are computed from the covariance matrix. And like I said, eigenvectors and eigenvalues can be computed if we are given a matrix. And this matrix we consider is the covariance matrix from step two. There are again a few libraries that we can use for it. For example, matplotlib is a very popular library in Python that we use for performing principal component analysis. Okay, now coming to the career path and job opportunities. So as you know that in the modern days, uh, we are so much developed. We have been working with data, big data, and we have been trying to analyze them to get results. For example, you can see many machine learning and deep learning algorithms and natural language processing. For example, if you go to a big company's website and you have some customer issues, you have to simply call them or have to talk with their chat assistant, right? So these chat assistants are basically one sort of artificial intelligence. What they do is that they're automated. So whenever you're typing something, they are taking important words from them and clustering them together in order to get the gist of your question or your query. And then they have some solutions prepared already. According to your query, they give you the answer or the solution. Similarly, for big companies, you have seen text to speech, uh, which is very helpful for many different aspects. Let's say people with disabilities or old people. Uh, if you type something, it basically speaks out, right? Similarly, artificial intelligence in smartphones, you can see, for example, Google Assistant or Siri, they use their own artificial intelligence. And if you have any queries, you talk to them, you speak, and they grasp that, and then they give you an answer corresponding to that. So all these things are a part of natural language processing. We implement it everywhere, starting from an AI driven vehicle to text to speech, everything. In general, natural language processing is a field concerned with interaction between computers and human language, like I have just said. Similarly, what is deep learning? If you are given machine learning algorithms, and if you are given more than one machine learning algorithm, let's say you have 10 machine learning algorithms, that is what creates deep learning. So deep learning is multiple machine learning algorithms. And for most of the critical jobs in industries and everywhere we see, they each of them have deep learning algorithms implemented. Even we use deep learning in order to deal with natural language processing. And these days, these are the fields that we aim for. I mean, these are our future. Everything is getting automated, and we have to deal with them in such a way uh, that works. That is why we're learning these algorithms and stuff. In order to do that, mathematical and statistical knowledge is extremely important. If you don't know what is going in the back end, you will struggle. Even when you are given few libraries or few softwares that do the work for you, you still might face many complications in order to implement them. Or when you are given a data set, in order to visualize them, you will struggle, because if you don't know the what is going on in the back end. So that is why we need mathematics and statistics. And in mathematics, linear algebra is something unavoidable. We really can't, because we already have seen how important it is in order to deal with the current computing algorithms. Therefore, to do well and to expedite in the field of computer science or physics or modeling, or even like modeling a data for the pandemic, let's say the current situation going on, we need linear algebra as it plays a vital role. So that's it about the webinar. Thank you for listening.